Okay, welcome engineering statics students. For this mini lecture, we're going to look at getting a equivalent force and position of that force resultant for this distributed load on a beam. So our beam has a length of L and it's presumably being anchored with some kind of support, probably a cantilever support in the wall. We can imagine it sticking out of the wall here at point O. And the load distribution follows a cosine function. And we can take a look at this and just kind of verify that it makes sense given the graphic. If we put in an x equals 0 over here at the wall, we have a 0 for x and the cosine term becomes 1. And so the load in something like newtons per unit meter is W0 over here. W0. And then if we put in L at this point for x, the L's cancel, we get pi over 2. We have cosine of pi over 2, which is 0. So that looks right given the graph of our load distribution. So we can use our relationships between distributed load functions and force and moment using basically summing up of little bits of force under that distribution and then summing up the moment contributions from each of those little bits of force at their respective locations from our reference point O to get the resultant moment, and then divide that moment expression by the force expression and hopefully get a position where we can put the resultant force. So we're going to define this time our force, and by definition this distributed load goes all the way to L. Something that you can look at later are conditions where maybe that distributed load doesn't go all the way and you can integrate over part of the beam if maybe the load didn't go all the way, but in this case we know the load is being applied over the whole beam. So we can say our resultant force is going to be the entire distributed load from x equals 0 to x equal L of distributed load. And at this point we're just looking at the magnitude. If we were going to define a vertical coordinate direction, we might say that this should have had a negative to indicate it's downward. But at this point we're gonna keep life simple and just be looking at magnitude. We know that it's going downwards, so we can just draw that on the figure after the fact. So here's our load per unit beam length. And here's our incremental differential length of beam. So we have a force per unit length and then we have a length, so this should give us force. So we can define our force resultant as that integral, which should be W0, there's our constant, and the integral of cosine is sine. And of course we have to put a multiplier out front to account for the fact that we don't just have x in the argument of the cosine. So before we put our limits of integration back over here, let's just take a really quick check and make sure that if we take the derivative of this, we get the argument of our integral. So again, the derivative of sine, say of u, should be cosine u. Derivative of sine is cosine, no negative, and then we will end up doing the integral of the argument, or excuse me, the derivative of the argument with respect to x. So we'll throw out a pi over 2L, which will cancel with this pi, and we should be left with cosine of the argument just times w. So that checks out. So we can evaluate that expression between L and 0. So we end up with a W0 times 2L over pi times sine evaluated at L, which the L should cancel, then it should give me pi over 2, which is 1, minus sine evaluated at 0, which is 0, which should give me a W0 times 2L over pi. So that is the magnitude of the load applied to this beam by this function for the entire function over the whole beam. Okay, so in order to know where to put it, we now have to calculate the effective moment due to that load distribution. So for that, we go back to our distributed version of the moment of the sum is the sum of the moments. So we're going to define a sum of the moments here, which is going to be, again, we're going to look at 0 to L, and now we're going to define a small bit of moment, which is going to be x. There's our radius, and here's our incremental bit of load, just like we had in the load distribution. Pi over 2L x dx. So here's our moment arm, or our radius, and here's effectively our df that we've already defined. So this is a bit of moment, and we're going to integrate all the bits of moment from 0 to L. So we can actually rewrite this as just W0, make it a little simpler. And the first thing we're going to see is, oops, this is not nearly as simple of an integral to evaluate as the other one. So we're going to have to go back to our calculus roots and pull out an integral trick here. So x cosine x, basically. You can look that up in a table of integrals, or you can use integration by parts. So if we want a real quick integration by parts here, we can identify, we'll call this u, and we'll call all of this dv. And we can remember that by IBP, we can rewrite this integral as uv minus the integral of v du. And why did I pick that? Because if I define x as u and then I write a du, I get rid of that x, and then I'm left with the integral of a trig function, which I know I can handle. So now the trick becomes just making sure we don't mess up a sign, or make sure we keep our constants defined the way they need to be. So let's rewrite this in this form, going back to, and I'm going to hold our multiplier out front and not continue that through the integration, because that's another term that we would just have to be rewriting. So I'm just going to be writing the integral portion here. So we've got a u, which is x, and then a v, which is the integral of this term. So cosine of pi x over 2L dx would be the term that I would take the derivative of with respect to x to get this. So that would end up being what is the integral of cosine? Again, we saw that up here. It's going to be sine, but but we have to deal with our constant, so we end up with a 2L over pi sine of pi x over 2L. And we can just take the derivative of this to make sure we get that. So we end up taking that constant, comes out front, and then derivative of sine is cosine, no negative sign in this case. Okay, minus the integral of v du. Okay, what's v? Okay, we just wrote v right there. Du is dx. So we can write 2L over pi sine pi x over 2L dx. So we got a v and we got a du. And let's just take a quick check. uv, minus integral of v, here's v again, du. Okay, and this is all going to be evaluated. We'll write this way over at the end. Both the front term and the integral over our limits of integration. So we got to remember to apply that to everything. So we're gonna rewrite down here a little bit of math. Just for simplicity, we're going to roll back in this W0 because this is our coefficient on the front of this distributed load. So let's not forget about that. That kind of gives magnitude to the whole thing. But just some math simplification. We've got a 2L over pi here, and we got a 2L over pi here that are both that can both be factored out of our front term and our integral. Let's combine those two with our W0 right out front, and I'm going to switch colors again. So let's put those together. Let's do a W0 times 2L over pi. And that's going to multiply by everything. So we're going to end up with an x sine of pi x over 2L minus this integral, and without that front term. So it'll be just, we'll just rewrite this again, minus the integral of sine pi x over 2L dx. And again, all this is going to get evaluated from 0 to L. So let's make sure we factored those terms out. We had our W0, which we're going to bring back in, that was implicitly distributed over this whole thing, and we have 2L over pi. Take that out, we're left with x sine pi x over 2L, x over 2L. And we took the 2L over pi out of the integral. Integral is still being subtracted, and we should be left with the sine pi x over 2L dx, which is what we have. Okay, so let's go ahead and evaluate our integral. So we still got the x sine of pi x over 2L minus, okay, so the integral of sine is going to be negative cosine. And we have to take account of our multiplier term. It's kind of fraught with opportunities for sign errors. That's one of the difficulties with trig functions, is you're throwing out a lot of signs as you integrate and take derivatives. So let's just do a double check. We had a negative sign here and it had a negative sign here. Let's take the derivative of this just to make sure. We know that the derivative of cosine is negative sign. So we're going to have a negative to restore that to our positive, and then we're going to throw out a pi over 2L, which will cancel with this. So we should be good. Let's just rewrite this again to clean up some of those negative signs. Simplify, because we're going to have another crop of negative signs as we subtract our lower limit of integration. This is definitely a definite integral, haha, pun intended, plus 2L over pi cosine. So we're already seeing that we've got a sine term and a cosine term, and we're integrating over limits that are going to give us arguments of those trig functions that are going to look pretty close to 0 and pi over 2. So whether this cancels all to 0 or gives us what we think should be a moment going into the whiteboard is going to depend on, did we get all our signs right? Okay, let's drop in our upper limit of integration. And I'm just going to look, I'm going to change colors again, just try to make things a little more clear. We're now evaluating limits of integration. So if I drop L in for x, I'm going to get, for my first term, I'm going to get L times sine of pi over 2 times L over L, which is 1. And then I'm going to add L in this term, so I will end up with an L over L, which is 1, which leaves cosine of pi over 2, which is 0. Then I'm going to subtract my lower limit of integration, which is going to start with 0 substituted for x sine of x over pi x over 2L. Well, 0 in for x means this term's 0 regardless of what's going on with the sine term, so I know that's 0. But if I put 0 in for this term, I end up with cosine of 0, which is 1, which just leaves my 2L over pi term. So I'm going to have minus 2L over pi. So I can, again, rewrite this yet again. So we end up with a little bit of a complicated term that, may not have a lot of intuitive meaning. L minus 2L over pi. But we can rearrange some terms. So we can factor out an L. And we'll change color again. So we can say 2 W0 L squared over pi times 1 minus 2 over pi, and that's about as good as we're going to get. What we can do is now look for signs, because we do have some idea of which way we want our moment directed. So we've kind of evaluated the moment such that if our force was positive, was a positive number, it's downward, but if we call this a positive number basically, and cosine over the range we've put in should be giving us positive numbers, we'd be defining a positive moment. So given that we have not put a downward direction on that force, we know our moment should be positive given that. So we know that this number is positive effectively if we've defined the cosine term to be positive. Anything squared is going to be positive. So if this term is greater than 0, we've got one check at least that our moment term is correct. So pi is 3 and a bit. So you've got something like 1 minus 2/3. This is going to be a positive number. So we've got a pretty good idea that this is a good expression for the resultant moment about 0.0. So if we want to know where to put our distributed load force resultant, we would say x sub r, location of the force resultant, which just so happens to be the centroid of the shape defined by that distributed load, the area under that. So we know it's going to be like this side of the midpoint, give or take, should be m sub r over f sub r, which is going to be this big term, our moment term, 2w0 L squared over pi times our 1 minus 2 over pi, our moment, all divided by w0 times 2L over pi. So we can start canceling things. We can cancel some pi's. We can cancel that. We can cancel the 2. And we can cancel an L. So this is going to end up being L times 1 minus 2 over pi, which is looking reasonably good because we know this value is approximately 1/3. So if we were to define 1/3 of the way, you know, that's not a bad approximation. Kind of a sanity check on where the centroid should be. If we'd gotten a number out here, we'd probably start error checking. So if we were going to design a support at moment O, the values that we would be looking for, I'll go back to another color here, would be a force resultant. We would, if we were going to use a cantilevered support, if this were bolted into the wall, this wall support would need to be pushing up with this much force, and it would need to be exerting a moment, an opposing moment, equal to this. So the wall would have to push up and twist back in order to keep this beam in static equilibrium. So that is it for this mini lecture and adventure in integration by parts review in order to get our equivalent moment.